A tunnel is not just a hole in the ground. It's one of the most complex structures humans know how to build. It can run under cities, mountains, rivers, even the sea, and it must stay safe for decades. So why do we build them? Tunnels shorten routes, avoid obstacles, reduce traffic on the surface, allow metros and trains to pass under cities, protect nature above, and connect places that would otherwise be hard or impossible to reach. Without tunnels, we would have endless detours, crowded roads, and slower transport. If you like similar educational content, please like, subscribe, and share the video with your friends. But tunnel construction begins long before anyone touches the soil. Engineers first have to understand the ground. They study what types of rock are underground, whether there is water, whether the ground can slide, and which alignment is the safest. Geologists drill exploratory holes, collect rock samples, create 3D models of the subsurface, and simulate what will happen once the excavation begins. A single mistake can cost billions or lives. Then designers step in. They decide how wide the tunnel will be, whether there will be one tube or two, how ventilation will work, where emergency exits go, what structural system can handle the pressure of the ground. Only when everything is calculated, approved, and planned can the most fascinating part begin actually digging the tunnel. But there isn't just one way to do it. Engineers use different methods, from giant TBM shields that eat the ground continuously, to classic step-by-step excavation with immediate support. And that's exactly where we start in the next part. Once the tunnel route is chosen and engineers know what kind of ground lies below, one decision shapes the entire project: how the tunnel will actually be excavated. There is no universal solution. Each method works best in different conditions, so specialists study the strength of the rock, the amount of groundwater, the depth of the tunnel, its length, and what sits above it: a city, a river, or a mountain. In long, deep, or urban tunnels, builders often use gigantic machines called TBMs, tunnel boring machines. Imagine a steel cylinder as long as several houses, with a rotating cutting head at the front. It grinds the ground away while, behind the cutting head, workers install curved concrete rings. The tunnel grows forward, already supported and sealed. The advantages are clear: fewer vibrations, high safety, and steady progress. The downside is cost. TBMs are extremely expensive and really make sense only on large projects. In other places, the conventional method, often referred to as NATM, is better. Here, the tunnel is excavated slowly, section by section. A short piece of ground is released, the material is removed, and the walls are immediately reinforced. Shotcrete, sprayed concrete, steel ribs, and rock bolts create support that adapts to the real behavior of the ground. This approach gives engineers great control. They can react instantly if something changes. Where the tunnel is shallow, for example, under a street or park, builders sometimes use cut and cover. They dig a large trench from the surface, build the tunnel box inside it, and then cover everything back up. It's simpler and cheaper, but only works where you're allowed to open the surface. Before any of these methods start, the site must be prepared. A deep launch pit is excavated, access roads are built, power and water are installed, and areas for storing materials are created. Monitoring systems are switched on from day one. Sensors measure movements of the ground, pressure, moisture, and vibrations. If anything behaves differently from what was expected, the work stops immediately and is investigated. Then comes the symbolic moment: the first cut into the ground. A thin layer is removed. Engineers watch carefully how the soil or rock reacts, and temporary support is added almost right away. From that point on, the work settles into a rhythm that will last for months: excavate, clean, measure, support, check, and repeat. In the next part, we finally get to the heart of it: what tunneling looks like day by day, how machines move forward, how concrete linings are built, and what happens when water, weak ground, or cracks appear underground. Once the tunnel starts moving forward, everything works like a carefully choreographed routine, but with one important caveat: every single meter is different. Work begins at the tunnel face the point where the ground is actually being opened. If a TBM is used, Its rotating cutting head grinds the soil or rock, while conveyors carry the material backward. Right behind the machine, crews install the precast concrete segments. These rings fit together like giant puzzle pieces, sealing the tunnel and giving it strength. Step by step, the underground tube grows longer. With the conventional method, the process feels more hands-on. A small section of ground is loosened sometimes with small, precisely calculated blasts, then it's cleared away. Immediately afterward, the fresh surface is covered with sprayed concrete, strengthened with steel ribs, and secured with long bolts drilled deep into the rock. The rule is simple. Everything that's excavated must be supported right away. Unexpected situations are part of the job. Groundwater may rush in. Soft soil can start to collapse. Rock can crack in places no one predicted. When that happens, work slows down. Extra layers of concrete are added, cracks are injected with cement, drainage pipes are installed, and the area is remeasured before progress continues. Underground, patience is safety. Surveyors check alignment constantly. They verify whether the tunnel is still pointing exactly where it should, whether it is settling, and whether pressures remain within safe limits. On the surface, sensors monitor buildings, roads, and utilities to ensure the surrounding city isn't being damaged. As the rough shape is completed, attention turns to the inside. A smoother final lining is built, drainage channels are installed, and openings for future cables and pipes are prepared. Little by little, a messy construction site transforms into something that begins to look like a finished infrastructure project. But we're still missing the systems that make a tunnel truly usable: ventilation, lighting, fire protection, and control technology. Without them, a tunnel would simply be a concrete cave. And that is exactly what we explore in the next part. When the main excavation is finished, the work is far from over. In fact, this is the stage that determines whether the tunnel will be truly safe for the next several decades. What happens now is less visible, but absolutely critical. The first big topic is ventilation. Inside a tunnel, exhaust gases, heat, and moisture can build up very quickly. Engineers design powerful fans and duct systems so that fresh air constantly moves through the space. The airflow is calculated for everyday traffic, but also for emergencies. In case of fire, the system can change direction, pushing smoke away from people and toward exhaust shafts, giving everyone time to escape and rescuers time to react. Then comes lighting. A tunnel receives normal lighting, emergency lighting that works even if power fails, and guiding lights that clearly show the way to exits. Every lamp is documented and connected to the control system, so maintenance teams always know what is happening. Evacuation routes are another crucial layer. Along the tunnel there are cross passages, protected rooms, and separate escape corridors. Fireproof doors, clear markings, communication points, and cameras help people find safety even in stressful situations. Nearby, fire hydrants, extinguishers, and sensors are ready long before the tunnel ever opens. Fire protection is integrated into every detail. Materials are chosen so they do not feed flames or release toxic smoke. The concrete lining may be specially treated to withstand extreme heat. Cables run inside sealed channels. Openings are closed with fire barriers so that flames and smoke cannot jump from one section to another. At the same time, detection systems constantly watch for temperature changes and smoke particles and immediately alert the control center. That control center is the brain of the entire tunnel. Operators see live camera feeds, data from sensors, ventilation status, traffic information, and emergency messages. With a few commands, they can close the tunnel, change ventilation, activate alarms, or call emergency services. Before opening day, the operators practice dozens of scenarios so that in real events they react automatically and calmly. Once all installations are finished, the tunnel goes through a long series of tests. Ventilation is tested at different speeds, emergency lighting is switched on and off, backup power is checked, fake fires are simulated, communications are tried out, and coordinated drills with firefighters and rescue teams take place. Only after everything works repeatedly and reliably does the tunnel receive permission to open. When drivers finally pass through, the whole journey takes just a couple of minutes. They rarely think about the geologists, engineers, workers, machines, and thousands of decisions hidden in the lining and cables around them. But that invisible work is exactly what makes modern tunnels possible and safe.